Hi, I'm Baker. I'm a PhD student studying underwater robotic perception in Dr. Jane Shin's lab. This lecture will cover the basics of linear algebra that you will need to be successful in learning control theory, particularly in being able to understand and apply the state space representation of a control system. This will be the first of 2 short lectures. So what are unit vectors anyways? To find out, we'll start off with a vector x of 2 dimensions, 3 and 4, and let's draw this. So what does this look like? We have a length 3 in the x dimension, and then we have a length 4 in our y dimension. Now, what if we wanted to find the magnitude of this? We simply use Pythagorean's theorem, correct? And that is the distance from our start to our finish. So what is this magnitude? You take your x component, square it, and add it to your y component squared, and then take the square root. This is equal to the square root of 25, which comes out as 5. So we know we have a magnitude of 5. If we wanted to denote this, we would say the magnitude of our vector x is equal to 5. So I think you probably can determine that this is not a unit vector. To be a unit vector, think unit circle. It needs to be a magnitude of 1. So how do we do that? It's pretty simple actually for our vector x here to make it into a unit vector. All we have to do, and we denote unit vectors with a cute little hat like that, we take our x vector and we divide it by the magnitude. And this will get us our new unit vector. So we're simply dividing by this value 5 for each of our components, 3 over 5 and 4 over 5. Now our vector will be of magnitude 1 and fit onto our handy unit circle, just like that. Next, let's talk about the dot product. The dot product, also known as the scalar product because it results in a scalar value, measures how much 2 vectors point in the same direction. Let me explain what I mean by this. And let's start by building some intuition. So if we have 2 orthogonal vectors, 1, 0, and 0, 1, where orthogonal just means that they are perpendicular to each other in this case, and the dot product is a measure of how much they point in the same direction, well, these 2 vectors are about as far as you can get from pointing in the same direction. Therefore, their dot product ends up being 0. Let's break this down further using the equation. You can define a dot product between 2 vectors as, let's call them A, and we'll call this one vector B. Vector A dotted with vector B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. This cosine gives us some more information. What do we know about the cosine? Well, the cosine oscillates between 1 and 0, right? And we know that when theta, the cosine of theta is equal to 0, that's when it takes on its maximum value. So what does that mean for our 2 vectors up here? Well, if the angle is 90 degrees, then our cosine is going to, cosine of 90 degrees is equal to 0. And therefore, we are going to have a output of 0 here. Now, there's also another way that we can calculate the dot product between 2 vectors. We can take A dotted with B and directly compute their dot product. I'm going to write this out more explicitly to explain some other rules relating multiplication between vectors. So if we have vector A, which is 1, 0, and we want to dot it with vector B, which is 0, 1, we can't just outright do this computation. Why? This vector is 2 rows by 1 column, 2 by 1. This vector is also 2 by 1, 2 by 1, 2 rows, 1 column. You cannot multiply 2 vectors together if their inner dimension, these two, don't match. So we have to do something in order to make it so that the inner dimensions match. What we can do is something called the transpose. So we will transpose A, we demark this with a little t, which essentially rotates our vector. It does the same thing for matrices. So now we have 0, 1 dotted with 0, 1. Sorry. 1, 0 dotted with 0, 1. And what is the result here? So if we want to do the computation, we go along the rows and then down the column in our multiplications. What I mean by this is we take this term multiplied by this term plus this term multiplied by this term. So first with first, second with second, 0 with 1, we end up with the same value of 0. Next, let's explore the idea of the matrix. So why are matrices useful, and why did I write what I did on the board so far? Well, it's because this and this are system linear equations, and these matrices and vectors all together are the same thing. It's another way that you can represent a system of linear equations. Let me show you how this works. So if applying what we just learned for multiplying two vectors together, we can do the same thing with a matrix and a vector. So here we have a 2 by 2 matrix and a 2 by 1 vector. We see that our inner dimensions match, so we know we can do this. And if we look at these two numbers, this gives us what the dimensions of our result will be, 2 by 1, which that matches with what we have here, 2 rows by 1 column, another 2 by 1. So we can solve this by multiplying row by column and then row by column. So if we do 2 times x, we have 2 times x plus 3 times y. Then the same thing for the second equation, 4 times x plus 5 times y. And we know that that is equal to the output of this equation.